So, hello everyone, this is Swati from Aeronautical Engineering. Today we are here for the subject called gas dynamics. We have the seminar topic called analysis of hypersonic lift body performances using numerical solutions to perturbation equations. So, analysis of hypersonic lift body performances using numerical solutions to perturbation equations. Introduction to hypersonic flights. Hypersonic flight refers to the speed greater than 5 times the speed of sound. At an extreme speed, air behaves differently and traditional aerodynamic theories often fail. The design of hypersonic vehicles must consider heat effects, shock waves, and the air chemistry. Understanding how a lift body performs under these conditions helps engineers improve flight safety and efficiency. Numerical analysis using perturbation equation offers a way to study small disturbances in the airflow around the vehicle, helping to predict stability and control characteristics with high accuracy. Concept of lifting body. A lifting body of a vehicle is generates lift mainly from the shape rather than using large wings. The design is very useful in hypersonic flights because wings can overheat or fall at extreme speed. The smooth curved body helps distribute pressure evenly. The reduced drag energies use lift bodies for re-entry vehicles and advanced spaceline. By analyzing how these bodies perform using mathematical models, designs can improve their aerodynamic efficiency. The study focuses on small changes in airflow that can greatly influence lift drag and overall flight stability. Okay. Importance of numerical analysis. Numerical analysis plays a major role in studying hypersonic flight since it is difficult to perform experiments at such high speed. Computer simulations are used to solve complex equations that describe airflow behavior. These equations cannot be solved easily by hand because they are nonlinear and involve multiple variables. By using numerical methods, we can approximate the solution for real flight conditions. The result helps research understand how small changes in shapes, angles, or speed affect performances. This approaches save the cost and reduce the risk associated with physical things. Understanding perturbation equations. Perturbation equations describe small disturbances or deviations from a steady state in hypersonic flow. Even tiny changes in pressure, temperature, or velocity can lead to large differences in performances. By studying the small disturbances, engineers can predict whether a vehicle will remain stable or become unstable during flight. This equation simplifies complex aerodynamic models while still giving accurate results. They are especially useful for understanding how a lift body reacts to gust control inputs or structural vibrations during hypersonic travel, where precision is extremely important. Flow characteristics at hypersonic speed. At hypersonic speed, airflow becomes compressed and heated due to shock waves forming around the vehicle. The air even the air may even start to ionize, creating plasma. This affects changes how lift to drag behaves. The boundary layer, the thin region near the surface, can transitions from laminar to turbulent flow, affecting stability. Numerical solutions to perturbation equations helps model this effects more precisely. Engineers use them to predict temperature distribution, pressure variations, and shock wave patterns. Understanding these characteristics ensures the design can handle the extreme condition of hypersonic flight safely. Mathematical model in hypersonic analysis. To analyze hypersonic lift bodies, mathematical models are developed using the fundamental equations of fluid dynamics, such as Navier-Stokes equation. This equation describes how mass, momentum, and energy moves through air. However, due to complexity of hypersonic flow, simplifications like perturbation methods are applied in this method. Small variations from a steady flow are studied using approximations. These models are then solved numerically using computer algorithm. The resulting data helps predict aerodynamic coefficients such as lift drag and movement, which define the overall vehicle performances. Boundary conditions and stability. Numerical analysis setting accurate boundary condition in is essential. This defines how the air interacts with the vehicle surface and how disturbances behave at the edge of computational domain. Hypersonic lift bodies conditions include shock waves, wall heating, and surface friction. Stability is analyzed by applying small perturbations and observing how they evolve. If the disturbance if the disturbances grow, the flow is unstable. If they die down, it is stable. Understanding stability helps in designing vehicles that can make controlled flight at high speed and harsh environments. Role of computational fluid dynamics. Computational fluid dynamics CFD is the main tool of solving perturbation equations numerically. CFD uses powerful computer to divide the flow field into small elements and calculate airflow properties at each point. This technique allows researchers to visualize pressure, temperature, and velocity distribution around the lifting body. CFD also helps in the optimizing shapes for better performances for hypersonic applications, especially high temperature gas models and turbulence models are used with CFD engines can simulate flight conditions that would uh, otherwise to be dangerous or expensive to test physically. Shockwave formation. Shockwave forms when air is compressed at hypersonic speed. These waves drastically increase temperature and pressure around a vehicle. They also contribute to aerodynamic heating and drag. Numerical analysis using integration equation helps model how these shock waves interact with the body surface with each other. Engines, engineers study the angle, intensity, and location of shocks to reduce unwanted effects. By understanding these details, vehicle designs can minimize energy loss and avoid structural damage due to extreme thermal loads caused by strong shock formation. Heat transfer consideration. Heat transfer is one of the biggest challenges in hypersonic flights at high Mach number. Surface temperature can rise above 1000 degrees Celsius. This affects material strength and vehicle durability. Numerical modification methods allow researchers to study small variation in temperature across the surface by predicting where maximum heat occurs. Engineers can design thermal protection systems efficiently. Cooling system heat resistance coating and specific material chooses on establishment. Maintaining proper temperature control ensures that the lifting body can operate safely during both atmospheric entry and high speed aerodynamic coefficients. The lift, drag, and the movement coefficients describe how a vehicle performs in flight for a hypersonic lifting body. This coefficient depend on the shape, angle of attack, and flow conditions. Numerical contribution analysis provides precise values of this coefficient under different situations. Small changes in geometry or flight angle can cause large efficient performances. By analyzing this coefficient, engineers can optimize design for better calibration and improve control. Reliable predictions of these values ensure the lift body can achieve stable, efficient, and safe flight at hypersonic speed. Influences of angle of attack. The angle of attack is the angle between the vehicle body and the airflow direction. At hypersonic speed, even small angles can cause major changes and lift drag using numerical calibration methods. Engineers study how the airflow reacts to different angles. They determine the best angle of maximum lift without causing instability or heating issue. The result helps in designing control surfaces and guidance systems. A correct angle of attack ensures smooth maneuvering, better stability, and improved aerodynamic efficiency during high-speed atmospheric operations. Flow separations and reattachment. Flow separations happens when the air detaches from the surface, creating regions of low pressure and turbulences in hypersonic flights. This can lead to loss of lift and increased drag. Numerical conditions analysis helps identify where flow separations may occur and how it is affects overall performances. Engineers can then modify the surface geometry to reduce the effect. The attachment of separation is also studied to maintain smooth airflow, preventing the Preventing or controlling separations ensure better aerodynamic efficiency. Reduce vibrations and improve structural stability during hypersonic missions. Pressure distribution. Pressure distribution plays a key role in determining lift and drag force. In hypersonic flight, the pressure changes sharply across the vehicle surface due to shock loss. Numerical methods based on vibration equations allow detailed mapping pressure field. Engineers can identify high pressure zones that contribute to lift and low pressure zones that causes drag. This understanding helps define the shape or body shape of the optimal performances. Proper management of pressure distribution also prevents structural overload and ensures balanced aerodynamic forces during high speed travel, leading to safer and more efficient structural consideration. The structural consideration of a hypersonic lift body must be withstand extreme aerodynamic and thermal loads. Numerical analysis provides data about where stresses and heat are highest. This helps engineers strengthen those areas with suitable material contribution methods. Also helps the study how small deformation in structure affect aerodynamic performances. A flexible body may change shape under alternating the flow behavior. Understanding this interaction ensures that the structure remains without excessive weight. Combining aerodynamic and structural analysis is vital to achieve both performance and safety of hypersonic speeds. Control and stability analysis. Maintaining stable and controlled at hypersonic speed is very challenging. Small disturbances can cause the vehicle to oscillate or lose balance. Numerical contribution equation helps predict how the body responds to such distribution. Engineers use this result to design control system that adjust surface or the thrust in real time. Stability analysis ensures the lifting body maintains steady flight even under extreme external influences like gust or thermal variations. The data also aids in developing autopilot system capable of handling complex flight dynamics using unique auto hypersonic vehicles. Validation and testing. Although numerical analysis is powerful, it must be validated. Yes, it means the internal test and flight data are compressed with simulation result to ensure accuracy. If the numerical model matches real world result, it can be trusted for the design studies. This process involves reliability and builds confidence in using evaluation based numerical methods. Experimental validation also helps refine turbulences and heating model making predictions more realistic, combining both approaches, numerical and experimental. Application in aerospace engineering. The analysis of hypersonic lift body has application in re-entry vehicles, missiles, and spaceplanes. Understanding performances helps in designing vehicles that can travel safely through the atmosphere at extreme speed. The same techniques are used in designing reusable launch vehicles that returns to Earth efficiently. Numerical perturbation analysis supports innovation in defense and space exploration, contributing to the further of high-speed transportations. These methods allow safer and lighter and more reliable hypersonic speeds while reducing uncertain and improving the accuracy of aerodynamic prediction. Conclusion. Analysis of hypersonic lift body performances using numerical solutions to perturbation equations is a useful approach in aerospace engineering. It combines mathematics, physical, and computer science to solve problems too complex for traditional methods. By studying small disturbances in flow, engineers gain insight into lift height, stability, and heat transfer. The result improves design for safety, performances, and efficiency. With growing interest in hypersonic travel and military systems, this research continues to advance technologies leading to faster, more reliable, and more sustainable flight systems for the future. So we have the input and output of hypersonic lift and pressure distribution on an gas output. And this is the CFD analysis where we can see the waves coming on an airfoil and the shock location of the strength, heat flux distribution, waves and the viscous drag plus lift. Thank you.